So the next video we're going to watch in our series is all about power. Now, what is power? Well, we think of power because we plug things in, electrical items in, and they do something, whether they produce heat, or they produce light, they produce sounds. So the general definition for power is the rate at which electrical energy is converted into whatever source we want. So is So if you think about this computer screen that you're looking at right now, well, it's producing light, so that's an example. If you have a really old monitor, you can feel some heat off of it. And if you listen really closely, you can hear the fans on it, so it's producing sound. So mathematically, the equation we use for power is that power is equal to the voltage produced times the current. So P equals power, and we measure that in watts, which is a capital W, not a small w. V, we're familiar with that. That's voltage. That's a capital V. And I represents current. And we can measure that in amps. Now, a reminder, one of the ways that we get to power is looking at the resistance of an object. And resistance is equal to voltage over current. If you need more details about this, see the previous YouTube video. But I is current in amps, V is voltage in volts, and R is resistance in ohms. So just like we did with our resistance problems, we're going to follow the guess method in every single one of our examples. Now that we've got multiple equations to work with, we're going to have to think about what the appropriate equation is to use. So, in this question here, a small TV is connected to a 120 volt outlet and draws 1400 milliamps of current. Calculate its power rating. Well, we can see right there, the V is equal to 120 volts. Now this area might be a little bit confusing for you. We've got 1400 MAs. So let's write that down. But we work with amps, not milliamps. So how do we do the conversion for this? Well, you should ask yourself right now, how many millimeters are there in a meter? Pause the video and think about it. Talk to the person next to you. So what you'll have realized is that there's 1,000 millimeters in 1 meter. Well, there's 1,000 milliamps in 1 amp. So 1,400 milliamps is also 1.4 amps. When you're converting from milliamps to amps, just like we did in class, you need to move the decimal point once, twice, 3 times. What do we want to know in this question? Well, we're looking for the power rating. We've only dealt with one equation that has voltage, or current, and power. So we're going to use P equals VI. So let's plug in our numbers. P is equal to 120, 1.4. So now 120 times 1.4. And we have that power is equal to 168 watts. So therefore, the TV uses 168 watts of power. So that's the first of 3 equations we're going to learn today. The second one we're going to learn is about energy usage. When we're looking at the energy usage of the item, we're looking at the rate at which electricity is converted to another form. So we can know that our TV in the previous case draws 168 watts of power. But how much energy it uses really depends on how long the TV show is that you're watching. So the equation we're going to be looking at here is that energy is equal to power times time. So time, which is down here, we're going to measure that in seconds. No, we're not. So in this particular case, we're going to measure time in hours. And as we learned previously, P is for power, and we measure that in watts. So we're looking at the power used and for how long. So E is energy, and we measure that in watt hours. Now typically things are measured in kilowatt hours. So we're going to have to be comfortable doing this conversion. Now what is that conversion? Well, we know that 1 kilowatt hour is equal to 1,000 watt hours. So an example how to use this equation. How much energy does a 60-watt bulb use in one day if it's on all the time? Well, let's list what we know. We know the power here is equal to 60 watts. Now in a day there are 24 hours, so therefore the time that it's used is 24H. What we don't know is the energy. If we're looking at an equation with energy, power, and time, we're going to have to use this equation. And I can't stress enough, make sure you're following the guess steps every single time. So now we're going to substitute these numbers in. So we plug in the 60, we plug in the 24, and then we're going to bring up our calculator. And that is going to be equal to 1440 watt hours. If we want to do the conversion on it, we'll realize that we have to move the decimal point once, twice, 3 times. And that becomes equal to 1.44 kilowatt hours. Therefore, the light bulb uses 1.44 kilowatt hours of energy. Now the last equation we're going to work with here is talking about the cost. So simply cost is how much money does an item cost to run. So our equation in this case is cost is equal to energy times the rate at which it's at the rate of electricity. So cost we measure in dollars. Now the rate, this is measured in dollars per kilowatt hour. So how much does the energy cost we get from our local power provider? And E stands for energy. And as we learned previously, that's measured in kilowatt hours. So the previous question, how much money will it cost if the rate for electricity is 0.08 per kilowatt hours? Well, let's see. We know the rate for electricity is equal to 0.08 per kilowatt hour. And in the previous question, we found that the energy on that light bulb we used was 1.44 kilowatt hours. What don't we know? We don't know the cost. So what's the equation we're going to use? cost equals energy times rate. And now we'll plug our numbers in. So now we'll bring up our calculator again. And we can see that leaving this light bulb on all day has cost us 11 cents. So the light bulb costs 11 cents. Now make sure to try the questions that you have on your question sheet and make sure at all times you're using the guess method for all of these questions.